Today we are going to learn like how to develop efficient algorithms, and basically we will learn is a terminology called Big O to using this way to determine if an algorithm is an efficient one or not. Suppose for example, we learned many algorithm before. For example, the search algorithm, we learned the linear search and the binary search. But which one is better? I mean, we have this question in the first exam, assignment. That we use this function to get the the time of the system, to determine which program runs faster. But actually, in real life, it's really difficult to determine which algorithms is better just based on the running time, because some algorithms their running time is depending on the specific the input. For example, linear search will be much faster than binary search if the element we want to search is just at the beginning of the list. So linear search will just find it directly, but binary search need to be divide the list into two and find it on the first and then second, and will be very slow. But actually, binary search is we know it should be much better than linear search. So how can we compare these algorithms? So we can use this idea called Big O. It's a notation that to measure the algorithm's complexity based on input size. So for example, similar for linear search, if the number is not in the array, so we need to compare every element in the array and finally decide, okay, this element is not there. This way, we need to compare, do n times comparison. And if the number is in the array, it could be at the beginning or at the end, but so on average, we need to at least compare half of the elements in the list to determine if it's there. So then this linear search is execution time is proportional to the size of the array, because average is to be half of the n. So if we use Big O to represent linear search, it will be O(n). It's pronounced as order of n. So we can usually just use O(n) to pronounce as O(n). Basically, it tells that linear algorithm, linear search need n times kind of manipulation to finish. And this Big O actually represents the order of the magnitude, overall how much time you need to finish everything, every operation. And this kind of O(n) algorithm is although you can see for linear search, it's O(n) seems it's just a very simple algorithm. It reaches O(n), but actually most times O(n) is already a very good algorithm. We will explain later. So this kind of algorithm is called linear algorithm. So another thing we need to mention is that for most algorithms, based on the input is different, so the actual execution time may be different. Sometimes, for some input, we will have best cases and running very fast. For some extreme input, it could be, for example, for linear search, that number is just at the very end of the list. That's the kind of worst case. We need to compare every element. So these kind of best and cases and worst cases, although they are not representative, it's not average. But if we know the worst cases of this algorithm, we will say, okay, this algorithm, no matter what, it can never be slower than the worst cases. So this kind of analysis is very important. So to determine the Big O, the order of the magnitude, there's two things we need to remember. We can ignoring multiplicative constants, which means for example, for that linear search, average it need n divided by 2 time operations to identify that number. But we can basically just remove this 0.5. And because it's a when n is a, I mean, when we use n, we mean it's like a very large number. So if n is very large, this divided by 2 actually doesn't have that many affections on the whole execution time. And also, I mean, for this big O, we usually want to know like the order of the magnitude, not actually the real number. So we can, I mean, On equals to On divided by 2 and O100, and they are all the same, just linear. And another thing is sometimes there are some like extra operation. So for example, this number finds the maximum number in an array. So yeah, if like we can just for example, if there are n numbers and the word we can just we just need to compare this number with the first n minus 1 numbers, right? If I mean sorry, we just need to search the huge number from biggest number from the n minus 1 numbers. As long as those ones are not the largest, we will know, okay, maybe the last one is largest. So so then if we like mean specifically they should be On minus 1, because we just need at most this many times of a comparison. But I mean, again, if n is very large, n minus 1 will be equals to n. So On minus 1 is On. So this is like the two features when we do use to compute this to determine the complexity of an algorithm. And similar to time complexity, we also have space complexity. I mean, just the same way, like using big O, but this time On means like, for example, it's a list. This list requires n the number of n elements on the array, like sorry, not on the memory. So that's very similar to On, except this time n means how many cells in the memory need to be allocated for this algorithm. We discussed this kind of, but why we need to know that? Actually, you can see this is a question from LeetCode. It marks it hard because they not only just let you to answer this question, but you need to answer give a function, I mean give a method that works on every O1. We briefly discussed O1 previously for that hash function, right? Because O1 is like there's just one operation. You just know the answer exactly, like at the moment you perform the function. That's ideal. Like you don't need to do any calculation. You just find it directly. But you can see this is marked as hard because it's very difficult to design such kind of algorithms. Yeah. So during your future like job hunting, if you're going into some good companies, they will have this kind of questions to, for example, design an algorithm using time complexity is log n. It could be very difficult. I mean, a normal algorithm like using a bunch of for loops, you can easily solve it. But building an algorithm with a specific complexity is very difficult. So let's see a few examples to try to figure out how can we determine this big O, how can we know the complexity. So this is this one, the for loop. This one is the most like basic one. So the time complexity is just the number of the operations this piece of code should be performed. So this one will be On, right? Because like from 1 to n, they do this kind of operation. So in total, you need n times of operation statement. Then how about this one? This is a nested for loop, right? So we have one loop here, another j less than or equal to n here. So basically, it's just for each I, we will do n times kind of n times calculation, and another I. So in total, the big O is just O(n) squared. So this kind of algorithm also called a quadratic algorithm. So I mean, of course, O(n) squared is less efficient than O(n), but actually most times the easiest way to solve a problem is just using a bunch of for loops. For some difficult question, you might even see O(n) like O(n) square, O(n) to the power of 3. That's like even complicated, but that's all we can do. So usually like for this statement k equals to k plus I and j, this kind of statement, the time required for this operation is just fixed, just determined by your computer. Like if a fast computer will run quickly, so we can just use a constant c to represent this, and then this can help us to calculate like what is the complexity of the entire algorithm. So let's see this example. Very similar to the previous one, except here is j is less than or equal to n, but this time the maximum number of j is determined by the number of I. So I equals to 1, j will just do one time. When I equals to 2, this for loop will do twice, right? So just determine. So what do you think? Anyone knows like what is the time complexity of this one?
Time complexity is order of O and Q.
Q? No. Why do you think it's Q?
I would say n squared.
Okay, yeah, that's correct. Yeah. So this one, like, although I mean, if this one is I is less than n, but we can actually do a calculation like when I equals to 1, there's only one time constant computation. I equals to 2 times. Say I equals 3 is 3 and 4. All the way when I equals to n, we need to do this statement for n times. And after some simple mathematics, we can see if the result is this formula, and we can remove the constants and remove the less determined part, and then it's still O(n) square. Of course, we know that. In real, when we run this program, this one may need less time because yeah, it's not n here. But that's how like time. I mean, this big O notation means it just tells you like the magnitude of the whole program. It doesn't say like how much time it operates. So let's see another example. How about this one? This time j is less than a constant number 20. Anyone knows what the big O is?
It could be the big O could be O order of n squared.
Still n squared? 20n. Yeah, almost correct, because 20n, we know 20n is just n, right? Yeah, but you are correct. Yeah. So it's just changing this to a constant number, the means the running whole like O(n) is much smaller. So I think okay. So this is another example. So we have a if-else statement. Although the if statement, there's only one like statement, but in the for loop is within the else statement. So overall, the complexity is O(n), because this one we need to know the worst cases of this algorithm. Of this pixel code. So sometimes the big O notation can only can also represent like a constant time operation. Like if the running time of the algorithm actually doesn't depend on the input size, then we will say that it takes constant time to do the kind of operation. For example, if we have a list, we just get the element by its index. So it's just O(1), we directly get that number. And also for hash, ideally, if a hash function is good enough, it should be give us the location of an atom directly. But of course, we know that there are many like collisions and all those things. It's not possible to get a O1 complexity hash. But yeah, that's like the ideal situation. Hash is also O1. Let's see another example. We talk about binary search, and for example, this question, this formula actually help us to determine what is the time complexity of binary search. So like assuming like n, because each time for binary search we divided this whole list of n elements into two parts, right? So this n should be, assuming we can divide it for like maybe k times. So n should be equals to 2 to the power of k. For example, if it's the n is equal to 8, k is maximum is 3, right? If we cannot further divide it. So we can basically take each time divided by 2, each time divided by 2, and c is like still the constant operation. So finally, we can use this formula to find out that the time complexity of binary search just log n, which is better than linear search, which is log n. Which is O(n). So another is example that the selection sort we learned before. So we know selection sort, you just find an element. If it's smaller than the previous one, we just the previous one we just swap it. So this basically each time the smallest number will be put at the beginning of the list, and each time, and then the second smaller will be put on the second place of the list. This way, all the way we can just find out, order this whole list. And similarly, like we just need to like in first time to find the smallest number, we need to search all the n-1 numbers. Second time, we just need to find check all the n-2 numbers and find the smallest one. All the way we can compute that in total we need O(n) squared time to finish this algorithm. So this table gave us some commonly see big O, like growth rates. And ideally, its constant time is better, but most times log n is already very good algorithm. And even n log n is very good algorithm. But the worst case is we have this kind of exponential algorithm, which is the worst. We be able to try to avoid this kind of algorithm. It requires extensive extensive time to finish the algorithm. So let's see another example. So this is also the final example today. We learned this finding greatest common divisor in asymptotic 46, right? So basically, two numbers, we find a number that is their divisor, and it's also the greatest one. For example, this one, 4 and 8, their greatest divisor is 4. 3 and 8, they actually doesn't have any common divisor except 1, so the largest one is 1. So then giving two numbers m and n, suppose m is larger than n, how can we find out this great common divisor? I'll give one bonus point for anyone if you know how to figure out this problem. We think we learned in 1046, right? No? Anyone knows how to solve this? By the way, the divisor means, like, for example, 8 divided by 4 equals to 2, and there's no remainder. In this case, we say a is divided by 4 is a divisor of a. If it's, for example, 8 divided by 3, the remainder would be 2, right? So then 3 is not a divisor of a. No one? Okay. Let me just show you the answer. So the most simple way is just we just compare all the numbers smaller than m and n. We check if it's a divisor. If it's a divisor of m and if it's a divisor of n, we just keep it and we search the next one. We just compare every possible situations until we find the maximum number. That's the way. I mean, the most simple way to do that. But of course, this is not. I mean, although the time complexity should be just O(n), right? We just search from 2 to n, right? We don't have to, even if we search every number, just time complexity is not that like worse. But we still can improve this algorithm. For example, so here this one, instead of search from 2 to n, we can actually search from n to 1, like search backwards, because we want to find like a greatest common divisor. Assuming for that 8, 4 example, we search for if we search from 2, it will be 2, 3, 4. We know, oh, 4 is the biggest. Actually, we want to find the biggest one, greatest one. We can just search from 4. 4 is already a great like a common divisor. We know any number less than 4, even if they are divisor, they cannot be the greatest one. So this way, we don't have to actually search everyone. We just need to find one divisor that's is common divisor, and we can break here. We don't have to check any other answers. But I mean, this is already very good. But can we still improve it? Anyone have any ideas you can improve this kind of? No, yeah, this is yeah, it is difficult. Yeah, so the thing is, we don't have to search from n. So it's divisor. So right. So
We can do if m divided by n, we can return 0. So we can return the n, the greatest common divisor. You have to look for the otherwise you won't be able to do that.
So let's take this example. So we assuming we want to find the greatest common divisor between 4 and 8. So it could be either it's 4, right? Otherwise, it cannot be 3 actually, because 3 yeah. So 3 is even if it's a divisor, it means divided by 2. The remainder will be 0. So at least this one should be smaller than 2, because how do I say that? Yeah, so if a number, for example, 2 is a divisor of 4, and you divide it, I mean, at least, sorry, if a number, let's see, s is the divisor of 4, at least it should be two times of s to 4. It could be 3 times of s or maybe 5 times of s, but at least it should be 2 times of s is equals to 4. Otherwise, it is not a divisor, right? If it's just 1 multiplied s by 4, it's the same. S will be equals to the same as 4. So we actually doesn't have to check start from n. We can just divide it n by 2 and start from there, because the number either is just n is just a divisor of m. Otherwise, it has to be some number smaller than n. So this is another way we can just using this way to further improve this algorithm. But actually, this is already very good, but actually this is still not the best. This guy Euclid is very like Asian people. It's 300 BC. He actually designed an algorithm that's even better. So like the idea is that if I mean the remainder is 0, of course, the greatest common divisor is n. That's simple. But otherwise, we don't even have to start from n divided by 2. We can compute. I mean, GCD of M and N actually equals to GCD of N and M and the remainder N. This is a little bit hard to but let's figure out why. So suppose I mean the remainder of N is R, then we can actually change this to this formula, because like R is a remainder, Q is a result of M divided by N, right? So we can just convert M to Qn plus R. So this way, any number, like if it's divisor of M and N, if it's a divisor M and N, it should also a divisor R. Otherwise, it is not a divisor. I mean, yeah, that means there could be some remainder. So instead of computing the GCD of M and N, we can just compute the GCD of N and this R, this remainder. So yeah, that's the algorithm he designed like not 300, maybe 2000 years ago. Yeah. So when we discuss this example, so you can see actually the brute force that like checking every possible situation, the complexity is O(n), and half of the still very good, and the complexity still O(n). And but this one it was even like yeah, it's even quicker, it's log(n). And actually the thing is, even the previous two, the complexity is O(n), but we know that the other one, like that only check half of the numbers, is better than the previous one. So yeah, so this O(n), sometimes I mean it's good to compare different algorithms. Like let's say your O(n) is better than theirs, but some situation, if they are the same, it is still possible that one algorithm is better than the other. So this is one thing to remember. I would say it's really difficult to find out O(n) sometimes. We will give some further examples next class to discuss how to define it. But actually, especially nowadays for those deep learning algorithms, it's too difficult. You know, the model, it could be a black box, and you don't even know how it's you don't only know the architecture, you don't even know how the training is performed. So some mathematicians, they publish their papers, they will give this kind of explanations and have an O(n) and okay, my algorithm is much better. But in most times, you don't even know. You just test a few examples and just using the running time to showcase that your algorithm is better. But this kind of thing is, it could be, I would say, just remember this typical, those classical like a binary search and tree. We will learn tree later, and what is the time complexity of the trees, because the recruiter will ask you these questions. You don't even need to tell them the calculation steps, but you have to give them the answer to make sure they you know this idea. So yeah, that's all about today's lecture.